Good evening, everyone, and thank you for listening to the Futurati Podcast, where we dive into how emerging technologies will impact the world and your bank account. I'm Trent Fowler, and joining me, as always, is my co-host, Thomas Fry. Thomas and I are futurists, keynote speakers, and consultants with decades of experience in analyzing trends and communicating new developments to audiences across the world. Reach out to us at futuratipodcast.com/contact-futurati if you'd like to hire us for consulting, to speak at your event, or to advertise on our podcast. Thomas, we just wrapped up an interview with Clifford Mapp, who is at a company called Dynex, and they are building a blockchain-based neuromorphic quantum computing platform to solve all the problems associated with optimization, with scheduling, with all the things that you would apply quantum computing to. And I went into it kind of skeptical because it just sounded like they were piling a bunch of stuff up that would make VCs excited, but wouldn't ultimately yield a lot. But I came away from it a lot more impressed with Clifford's technical knowledge and the direction that the company is moving in. How did you feel about the conversation?
So it's not just a buzzword company after all.
Yeah, there's a lot of technical depth there.
Yeah,
definitely the reading.
Yeah, they're working on some absolutely fascinating stuff, and we've brought up some pretty far-reaching concepts for them. And he seemed like ready and willing to dive into each one of them and give us his take on it. I thought that was quite refreshing. I think they have a company that people really need to pay attention to in the future because they're working on some far-reaching technology that's going to be entering our lives in absolutely fascinating ways.
Yeah, they're building
not the least of which is neuromorphic computing, which nobody knows what that is.
Well, it's biologically inspired computation. So you can have neuromorphic chips, or you can have neuromorphic networks. You can have algorithms that draw on research in cognitive psychology or cognitive neuroscience. So basically, it's a neuromorphic computing platform. It leverages heavy elements of quantum, and it's also based on a blockchain because they ultimately found that was a lot more scalable. So yeah, we talk about quantum LLMs, we talk about reinforcement learning, we talk about crypto and their approach to using the blockchain, we talk about applications of quantum algorithms in the future, and really it was just a characteristically wide-ranging conversation, I gotta say.
I thought it was great.
Yeah, so we hope you think it's great as well, and without further ado, this is our episode with Clifford Mapp. Tonight, we're joined by Clifford Mapp. Clifford is the global head of ecosystem development and information security at Dynex, the world's only accessible, neuromorphic quantum computing cloud for solving real-world problems at scale. Dynex is already supporting thousands of projects in health and pharmaceuticals, research, artificial intelligence and machine learning, architecture, aerospace, electric vehicles, and fintech. Clifford's pioneering work has been critical in developing Dynex's security and robust technological ecosystem, and his 20 years of expertise and experience in cybersecurity and programming ensure the integrity and resilience of Dynex's platforms and services. If you enjoy this interview, please subscribe to the podcast and share it with your friends. And don't forget to check out our website, futuratipodcast.com. Clifford, thanks so much for coming on the show.
Oh, you're more than welcome. I'm glad to be invited.
Let's hear a little bit about your background, your interests, and what brought you to working on the problems that you're working on today.
Yeah, sure. So I've got quite a varied background. For the last 20 years, I've focused primarily on cybersecurity and development. Although in the last, I'd say 18 months, my kind of focus has been more learning quantum and quantum algorithms.
Fantastic.
Have we figured out the whole quantum encryption problem yet? I mean, are we getting close?
Actually, me and one of my colleagues today were actually talking about this exact thing, strangely enough, about obviously, if we're going to do new types of encryption, quantum is probably where we're going to be seeing it from. Whether that will be this generation of quantum or what would be the next iteration of it, I guess there's only one way to find out, and that's to actually code it and try. So we're already working on a few quantum algorithms for encryption, showing some really impressive, like, potential, but much like anything, it comes down to how easy is it to implement, right? Because if we bring out something and it's completely crazy to implement, then nobody's ever going to use it. How are we going to license that, for one? Because obviously that's another big issue, right? You look at something like OpenSSL, for example, right? The reason why it got such an uptake was because they effectively open sourced the technology behind it, not the certificates, but the actual underpinning technology is open source. So we're trying to go down that same path where we're going to open source our encryption methodology. Now, obviously, if we build certificates around that, then we would need to work that out. But fundamentally, the underpinning technology is going to come out for free.
Beautiful, beautiful. We will circle back around to quantum encryption. That's something I think a lot about, and futurists generally are thinking a lot about. But I wanted to begin, Clifford, by just addressing what I think will be top of mind for our audience. So you work for a company called Dynex. Dynex bills itself as the only accessible neuromorphic quantum computing cloud, and I guess it's also a blockchain. So at first blush, this sure sounds kind of like a buzzword salad. So can we walk through the tech stack and get into the details? I mean, I think you want to justify each one of these things. Like, why does each part of the technology matter? Let's break down all of it. Neuromorphic.
I mean, what we can do is, if we give you a bit of a history as well of how we got to this, where we're at now, probably would make a lot of sense for why are we using blockchain, for example. Why fundamentally was, so originally 2 years before we even launched our own blockchain, we actually spent a lot of time working on FPGA technology to try and emulate the environment. We did, but what we quickly realized was that for us to do it on the scale that we're doing it at now would cost probably tens, if not hundreds of millions of dollars worth of investment to build out that kind of network. When you're talking about buildings that have got to house it, staff that have got to look after it, the expertise that's got to come wrapped around all of that. So, I mean, what we found out very quickly was we hit that 2-year window and we were just like, this isn't going to scale. If we're going to make this accessible to the masses, then it needs to scale appropriately. And of course, if we've got to spend $50 million every time we want to scale it up for more and more clients, sooner or later that gets to a really ridiculous number. Whereas using a decentralized platform or a blockchain made a lot of sense because we can onboard our own equipment internally, right? We can obviously onboard people who want to participate on the network. And not only are we securing our blockchain by having those devices on there, but our blockchain is actually really lightweight. It runs only about 10% of total resources on your graphics card to do that. So the other 90% was all ours to play with in the computational sense. So it really did sort of give us the benefit of both worlds. Plus, having that blockchain allows us to have a mechanism to pay for our network. Because obviously anyone who participates on our network actually has the ability to earn, obviously, our cryptocurrency that's the underlying technology. And then we've got trading pairs with centralized exchanges where you can obviously off-ramp that to actual currency.
So this is the first time I've ever heard a person say that they were using the blockchain for scalability. I mean, there are scalable blockchains, but yeah, I mean, it's famously not as scalable as a centralized payments network. So tell me a little bit more about the scalability issues you were facing, which were so bad a blockchain made sense.
Yeah, so I mean, FPGAs obviously are nice, but they are restrictive in the amount of workload that they can actually take, or you get into realms.
Can we define FPGA? It's field.
Yeah, sure. So a field programmable gate array, which is obviously a reprogrammable ASIC, which or an application specific integrated circuit. There's two ways you can look at that. Basically, an FPGA, for example, is a device that can be reprogrammed, right? An ASIC obviously has one specific burnt-in set of instructions. And then obviously you've got rendering on a graphics card, and working out problems on a graphics card, which can be as infinitely flexible because you're not locked into a specific set of hardware. We've got graphics cards ranging from like top tier stuff that's out right now all the way down to like 4-year-old graphics cards, because what we found is even the smallest amount of compute can be harnessed on our network, and therefore everyone gets the benefit of participation regardless of entry point. So you don't have to have mega money to get involved in what we're doing. You can actually have quite a modest investment and still participate in a you know, an acceptable way in that regard, because like I say, the blockchain barely uses 10%. The other 90% is ours to use for computational workload.
Okay, so you were trying to build this computational platform, it sounds like, out of FPGAs. It didn't scale well, and then I interrupted you. So you were talking about scalability. So let's
yeah, like, so obviously FPGAs are very restrictive technology, right? If you want to add to that or you want to upgrade it, then that's a whole nother set of investment. So the scale of being able to ramp up so that we can take on more clients or do more computational workload, it spiraled into silly numbers, right? So we very quickly realized that if we were to scale the size that we were expecting to want to scale, there really was only a few options for us. One was to partner with somebody like an AWS, right, who has the infrastructure there. But then we felt that we might be restricted on what we was and wasn't allowed to do on their network, right? Because it's not ours at that point. So it left us with one option, which was blockchain. And we came up with quite a novel approach. We took the same approach with our quantum set. So we entangled our proof of work side, so our blockchain side, and then our quantum emulation area that does all the simulation of quantum algorithms, or what we call POUW, proof of useful work. And we entangled the two together. So what do I mean by entangled? Basically, you can't do one without the other, meaning that the moment a machine is registered on our network for one side of the equation, they're automatically registered on the other side of the equation for proof of useful work. Thus meaning that we can not only secure our blockchain, but we can also run massive computational workloads all at the same time.
Okay. Now, tell me a little bit about what Dynex is actually trying to achieve. So that's scalability. The FPGAs wouldn't get you there. Well, I mean, what are you doing that requires this much scale?
So obviously, some of the biggest challenges that we've done so far would be something like protein folding. So an average human being's protein strings, around 300 amino acid, there or thereabouts. I'm not kind of a scientist in that regard from that perspective, but it's around 300 amino acid chains. And what we found was the amount of resources that requires to do proper protein folding is ginormous, right? On a magnitude I never thought possible, given how much resources Dynex has at its fingertips. To do 300 amino acid took nearly 40% of our network capacity. By far the biggest kind of workload we've run so far. But we've done some crazy things like computational fluid dynamics, or how air and liquid interact with an object in real time. We can do CFD simulations already, and those again, they use large amounts of compute, more than most people would ever use in their wildest dreams. But what we've found is that we are able to bend quantum to do kind of things that you wouldn't expect it to do. And that's really sort of fascinating to me, because for a long time, I assumed that quantum was locked to a very niche subset of products that it could ever be used for, right? But then when I joined Dynex officially and sort of was given sort of the rundown of what truly it's capable of, that that was a bit of an eye-opener to me, because we could, as long as it's built as an optimization problem, most things we can run. We've done some game theory, so like playing Sudoku or chess. We've really gone on tangents down quite unique paths, right, for quantum. Not many people are messing around with that because, and I mean, honestly, it comes down to the resources that are available. The number of qubits that you actually need to go and play a game of quantum Sudoku, where you're doing, not 9 by 9, but you're doing, 256 by 256 Sudoku. That uses more qubits than all of the quantum machines put together that are currently out there on the market.
Okay, so Dynex is a massive compute platform, it sounds like.
Yeah.
In most of the materials I've looked at, you emphasize the quantum aspect and the neuromorphic aspect. So I want to talk about, quantum again. I'm very curious as to your thoughts on the sorts of problems that are amenable to processing through quantum algorithms. I mean, we keep coming back to that, but the neuromorphic part is interesting to me as well. So, I mean, this is, again, a buzzword you hear. What is that? How is that different from classical?
You've got a few different types of quantum and how they're inspired, right? You've got what you would call a physical quantum, right, which is physics inspired. You've got neuromorphic quantum, which is biology inspired. So what do I mean by biology inspired? Well, what we know so far is that one of the most powerful PCs we've ever come across for a computational workload is the human brain. And for us, when we were mapping out how big our network got and what it would be capable of, it just made sense to use biology inspired methodology, because as our network grows, it's like almost like extra synapses being added to our brain, right? And therefore, the bigger our network, the more almost IQ the network gets, right? Using brain as an analogy, but the concept of parallel processing, and that's really where neuromorphic quantum algorithms really work well. Parallel processing is crazy. I've really had a bit of a deep dive and gone way down the rabbit hole too much in what parallel processing is truly capable of doing. But for anyone who doesn't quite understand that, like, we do that every day. We see something, we hear something, we smell something, right? It's all done autonomously. Your brain just knows how to do it. Well, now we're in the realm of where quantum algorithms can almost emulate the same procedures, where you can have one main core job being run, but a ton of these parallel processing jobs all feed in more data into the main process. So it really does lend itself to that whole mechanism of biology inspired.
Okay, so you can have neuromorphic computing on a chip level. It doesn't sound like you're doing that. It sounds like you're using GPUs, but you keep saying neuromorphic quantum algorithms. So I'm familiar with quantum algorithms, Grover's search or what have you. So, but how is a neuromorphic quantum algorithm different?
Sure. So neuromorphic algorithms and neuromorphic infrastructure in its own right is not new. It's been around for a while. D-Wave, IBM, they all run their own variations of these things. D-Wave actually pioneered the very first way that would allow you to emulate a quantum environment on traditional hardware. We're actually fully interoperable with D-Wave technology. So you can take something that you've already run on D-Wave and run it directly on Dynex and vice versa. It's 3 lines of code to change. That's it. We did that because actually, if you look at physical and then just slightly before physical, you've got what we would be, or simulated annealing is the best term for it. But a lot of people don't understand that terminology. So the easiest way is that it's an emulation area that allows you to run quantum algorithms on ordinary traditional hardware. Like I say, this is not new technology. It's just nobody's ever tried to implement it in a blockchain environment to decentralize the technology, so to speak. Obviously, for us, what we've found is that because there's so much capacity on our network, right, that we can utilize and adapt, say, IBM's KISS kit to run on our network. We can take D-Wave's package and run that on our network. We can run PyTorch. We're pretty much interoperable with a good, I would say, 90% of most machine learning packages that are out there. Plus, we've released a few of our own, actually. So, you could take our CFD package and in theory run it on D-Wave because of that interoperability. So we're trying to show that, making quantum available to everyone, not only does it need to be accessible with plenty of examples. At the moment, there really isn't that many examples out there to really get yourself like deep into it. But the other one is, obviously, we all know that if something's going to get mass adoption, it needs to be affordable. And that's something else that obviously we're really drilling home about. What we're trying to do is that we're not going to charge an hourly rate for our service, right? Most supercomputers, most quantum machines in general, they charge hourly. We're not. We're going to try and set it up for a whole new way of effectively billing out for computation. And that lends itself that if you bring in the per job cost lower, that barrier to entry lowers. And the more lower it is, we saw it with the portable PC, right? It went from portable PC to mainstream generalized PC in a very, very short time.
Right.
Because they dropped the price so low that regular people could afford to use it. And that's what we're trying to aim to do with quantum. But the best way to think of it is that if you were going to go and actually viably rent a quantum PC and you're going to be charged an hourly rate, what would work out better for you to keep paying that hourly rate, to keep on adapting your code? Or wouldn't you prefer to use something like us or D-Wave's technology where it's simulated environment and it keeps the cost lower until you're ready to actually pull the trigger on the physical, right? Because of the costs. So again, we can actually act as a stepping stone. However, what a lot of people are finding is like the simulated annealing and the emulation phase actually can provide just as much data these days as the physical. And there's so much less headache running an emulated environment than an actual like physical. You don't have to chill it down to absolute zero. You don't need a ton of people to actually be able to run this thing. Realistically, our network runs with a very lean staff group, and then the rest, it allows us to have some of the best developers in the world for continuing to push the technology forward.
Hello, this is Trent Fowler, co-host of the Futurati podcast. One of the most common pieces of marketing advice I've come across is to know your audience and give them what they want. One difficulty in podcasting is that it's actually pretty hard to do this. None of the major platforms give us any way to reach out to you, our listeners, to find out what you enjoy about the Futurati podcast and what you'd like to see done differently. So we've decided to record this commercial and ask you directly to reach out to us. Head over to futuratipodcast.com, go to the contact page, and drop us a line. Tell us about your favorite and least favorite episodes, what you'd like to see us cover in the future, and anything else you want us to know. We produce this show for you, and we want your advice so we can make it even better. Thank you.
Now, one thing I'm confused about is you said you're doing simulated annealing, which means you're simulating quantum states. But you also said that the proof of useful work system was entangled with other parts of it. So if you're not running real physical qubits, how are you actually entangling anything?
So the obviously the technology itself is like how we do our, as people call it, our secret sauce, right? Obviously we keep that slightly close to our chest, but it comes down to how our job scheduler deals with that tie-in. So for every action on one side, there's an equal and opposite reaction on the other side. And obviously that plays a balance continuously.
So
right?
Simulated entanglement?
Yeah, basically.
Simulated entanglement. Okay, cool. Thomas,
Yeah, and obviously we're the one thing that we're getting towards next is actually what we're dubbing our absolute entanglement, right? So we actually push the POW block hashing for the blockchain inside of the useful work. So it'll drop the energy usage by another 10% usage, which will make it even more attractive from an efficiency standpoint. But yeah, and then obviously it'll remove some of the headaches that we've had with the entanglement over the years.
Well, let me see if I got this right. So with Dynex's quantum computing costing around 12 cents per second, is that about right?
There or thereabouts, yeah.
Compared to IBM's $1.60 per second.
Yeah.
So what are the broader implications for industry and relying on high performance computing like this?
That's a great question, because we've had a couple of clients talk to us about this exact thing, about how the reason why they were put off at very first is because they look at the price and think that either we're not being truthful and accurate about what we're saying, or that it doesn't quite work as advertised, right? Both of those are inaccurate, right? The reason why we're able to bring that cost down is truly because of the lower overhead for our own infrastructure, right? We pay out for every job that's run on our network. It's a 70% goes to the infrastructure people, the miners that are running their equipment for us. The rest then goes into a pot. We split that up for a number of different things, but we end up with about 18%. So we don't take the majority of it, because we realize that actually the people running our infrastructure are the ones taking a large burden of the overhead, right, for running this. So of course we want to make sure they're properly compensated for that. And we're in the process, we just released it today actually, which is our subscription dispenser, which will actually do all of the dispensing, all completely autonomous, make sure that everyone's being paid what they should be. It's been a long time coming, and a fair number of late nights getting code checked and audited and making sure that everything is going to run smoothly. But yeah, today's been a manic day, because obviously we turn something brand new on and everyone's on, heightened alert for any kind of problem, even if it's just, the most silliest of things, because we want it to succeed. We've worked really hard to make this succeed. So every time we take that next big step, it's always a breathe in and hold your breath for a second moment for us, right? Because we put a lot of time and effort into this, and we don't want it to go wrong at all.
Yeah, of course. Okay, so am I correct in understanding that if you're using simulated annealing for the substrate, you're not messing around with photonic qubits or Majoranic quasi-particles, anything like that?
No. So obviously simulated environments, or our neuromorphic network, doesn't inherently let us run everything that a physical quantum can do, right? Obviously, a lot of people think that because we're doing simulated or emulated quantum, that we should be able to do absolutely everything a physical quantum can do. And obviously, that's not accurate. We're very open about that. We know that there will be certainly some edge case stuff that a physical quantum will just make us look slow. But then there's a few other optimization problems. Like Cubo, for example, doing quadratic binary calculations, right? Those will run amazing on our network because of the raw computational load set that we can run compared to, say, a physical quantum. So there's a trade-off for sure. We're still learning what we can and cannot run yet. Every time we think we've hit a roadblock, one of our devs comes out with some crazy new concept, and we go all around again. We're like, well, where's the next limit? So, nobody's ever tried doing, say, a quantum LLM at the moment. I can tell you the reason why, because the computational requirement set for doing LLM in a quantum environment is crazy. Like on magnitudes of scale, we're not even close to. However, doesn't mean you can't write translation layers to allow it to be run in Cubo and Hamiltonians and so forth, right? So Sam, our head of quantum architecture, he's been working on building this very first quantum LLM, for example, right? And there are certain things that we just never thought were even going to be possible to run. So something like NLP, or natural language processing, we assumed would be nigh on impossible until we built out something like Qiskit gates or D-Wave's own gate technology to actually provide that flexibility to actually produce that kind of data. But Sam has gone to show that realistically, you've only got to be stubborn enough and have enough of an understanding around the tech, and really it just takes time.
Okay, so this is something I haven't heard much about. What are the things that you can't do in a simulated quantum environment that become feasible with a physical quantum environment?
So there's a couple of examples. I may not be necessarily the best person to explain this, but a couple of our really high-end PhD sort of devs, Adam and one of our other guys, explained it to me that there are certain aspects, like we can do an emulated superposition, right? But there are certain things that inherently that come along with like physical quantum that we might be able to run them, but what you'll find is, because a physical quantum can, mimic full physics, right? So, molecular bonds and all kinds of crazy stuff. Although Sam did show me some molecular bonds and code this morning, strangely enough, about just such a thing. But, things like long-term simulations where realistically you need the physics aspect. We're biology inspired, not physics inspired. So there's obviously high level physics stuff is where it gets kind of murky, because you've got to, if it doesn't do it natively like what we're trying to do, then we need to write some kind of translation layer. That's how we did it with CFD. We wrote something to translate the computational fluid dynamic data into a Cubo, compute it on Dynex, and then translate it back to the software so that it understood it in its own language, basically. So anything that's high-end physics might have some issues. Now, like I say, we've not tried every kind of scenario on our network yet. We're getting there. Don't get me wrong, we're getting there. We just took on somebody that's very into the physics side, so she's going to be pushing that kind of research path pretty much now. She's doing she's doing an actual research paper on Ising models, Cubo, and so under Cubo, that'll be things like BQM or binary quadratic models, as well as discrete quadratic models. So she's really going to start pushing the boundaries of what we can and can't do. And then we're going to try and run a list of what we've found can work, what we've found can work with a translation layer, and obviously what we can't run, sort of thing. But right now, certain quantum gates type logic, we're still in the process of building that side out. IBM's new Qiskit version does make a big change. We're in the process of porting that over, as well as we're waiting for D-Wave to release their gate technology as well, so that we can implement that. And we just keep implementing more and more like machine learning algorithms at that point, right? The best analogy I can think of, right, is Dynex is a huge toolbox with many tools. We supply the tools for you to go make those amazing products, right? But it doesn't mean that we won't work with somebody if they're having a struggle. That's the benefit of, working very close with our community. We also keep very, personal and close ties with our clients. So if they get stuck, they can, drop us a line. We'll gladly help where we can. So yeah, but Claudia, her name is, she's a lovely lady. She's really, really brainy.
Yeah,
just
sounds that way.
she sort of fits in pretty well. She's just, one of the nerds, as we keep saying.
So how many people do you have working at Dynex right now?
So when I joined at the beginning of the year, it was 37. I think we're at 50 now.
So how many will that be when you have your quantum computing LLM working?
By the time
presumably you can automate a bunch of their work, so probably 5, 6.
Well, I mean, we've already said that we've invested in our staffing, right, to make sure that overall we have a wide range of different backgrounds and different angles of approach that they want to take quantum, right? I'm a security guy, so of course I want to look at it from encryption, security perspective. What could it do? You've got Sam, who's an architect by trade. So he wants to look at quantum architecture stuff for, diagnosing if a load bearing beam would actually hold up in a 100-mile-an-hour wind, for example. You can run that kind of calculation, obviously, in as an optimization classification.
Yeah. So can you share details about the record-setting computation involving a graph with 10,000 vertices?
Max cut problem. Yes, the max cut problem.
Okay.
That obviously NVIDIA held for a long, long time. They had to build out a massive network to put in their number. So we actually had to top out at 10,000. I think we've actually since pushed it a little bit higher again. But we top out because effectively the machine that's having to render all that data that's coming back effectively struggles to keep up because there's that much data. So to give you an idea, I tried to go for like 15,000 vertices. My machine dropped out and said, can't assign that size of allocation because the actual amount of RAM that my machine needed to return the data and reconstitute it to working data was like 290 gigabytes of RAM. So, it is crazy levels of magnitude. I mean, I literally have a full enterprise server beside me just so that I can obviously be able to do my job. But that's crazy that it needs even that. So again, that's that whole going back to some problems can be inherently brilliant on Dynex in an emulated environment, but there are times where quantum is obviously going to natively be able to calculate it. You don't have to have that extra piece of hardware to decode that data back, obviously, at the other side.
Right. So earlier you said that your people are thinking about all sorts of different angles to push quantum. And near the beginning of the conversation, you said that you had gone into this believing that quantum was a very niche application, very powerful, but only suitable for addressing a small constellation of problems. You've now changed and believe that, in fact, it's suitable for addressing a far wider range of problems. I was in the former camp. I mean, I think that it's incredibly powerful, but it's better for combinatorial optimization problems, certain kinds of factoring problems, CFD, things like that. So, I mean, what has driven that change? What are the problems that it can address? Yeah.
So I would say that personally, from my own experience, right, obviously, I've not just been working, I've been learning at the same time, right? Because I knew for a fact that, I was pretty in over my head when I agreed to do it. But I said to them, give me a year. I basically worked for free for a year so that I would not only have the benefit of working with the team and learning on the job, but equally so that those guys that I've been interacting with for the last year are all very familiar with the network, how it works, the intricacies of that side. And so I spent a year, or best part of a year, just just learning, like understanding differences between classical computation and quantum calculations and computation, right? I've had pretty much what I would say is a crash course. My ability now to conceptualize quantum algorithms is much improved from even 6 months ago, and I don't stop learning every day. Sam or Adam or one of our other devs like Ivan, they teach me something, whether they realize or not. I'm just absorbing it all and taking it all in, because I really see the potential and flexibility to utilize some of that technology in my own businesses over here in the UK. And up until I joined, I really didn't even consider quantum, because like you say, right, I thought it was just a very niche product that had very few applications except for very scientific use cases. But what we're finding is that really there's a lot of optimization problems that could fit a quantum type algorithm very nicely. Vehicle routing problems are a great example of that, right? You look at something like a logistics company like Amazon, for example. I could only imagine the computational power that they use just to work out where all of their trucks, vans, and delivery services are going to be for the next 7 days.
So do you ever see a point where we have personal quantum computers in our homes?
I think we're on that path. The way we end up with actual personal home quantum is when they crack actual room temperature quantum. I think that's the catalyst, right? In my view, anyway, that's the catalyst that drives, oh my God, look, now you don't need a building, you don't need a ton of LN2 or liquid nitrogen to cool this thing. You don't need huge amounts of resources to run this thing. We're seeing that happen. Now they're starting to try and work on room temperature quantum, and we're not quite there yet. I think we're still probably a few more years away from that. But a bit like how the CPU basically made a massive technological leap forward when they basically changed it from a ton of microprocessors to one unified centralized processing unit. We'll see that happen, I think, again when room temperature quantum hits the market mainstream.
Are you enjoying this episode of the Futurati podcast? If so, please like it, give the show a 5-star rating on Apple Podcast, Spotify, or wherever you get your podcasts, and share it with your friends. By far, the best way to help us grow is to spread the word on social media, which will expose our content to more people and help us continue to bring you interviews with world-leading experts in AI, quantum computing, cryptocurrencies, and so much more. Thank you in advance.
So do you see this being used on space capsules going to the moon?
That's really that. See, now that I like to sort of theorize about, because that's for me one of the most exciting parts about what Dynex is doing. Right, it's right on the bleeding edge of technology, and I think that when we get to the point where we've got that kind of technology, I think it'll be very advantageous to take that on any kind of scientific missions. We're only just starting to play around with dark matter, right? And being able to detect that kind of thing. Well, we know from our own experiments that, simulating dark matter environments is possible. And then being able to take that one step further, that's obviously what Claudia's working on right now. She's got her teeth into looking into dark matter research, which to me is another fascinating subject, right? I love reading up about projects down at the Large Hadron Collider. They're some of the most really out there research that's being done. And just for me, I'm looking forward to the next 5 to 10 years in technology wise, right? I would say in the next 10 years, we'll be probably seeing regular trips to and from Mars. We're going to probably have the start of a moon base at that point. And for all of those, things, we are going to need more and more computational power than we've ever produced before. And I just don't see how sticking with what we're already got, where we're right on that top of that von Neumann scale, where we can't shrink products any smaller, and we're reaching a point of where we can't push any more power through it. So at some point, that change needs to happen, whether it be quantum or a completely different new take on a PC. We don't know yet. There might be, something that comes along that wows all of us, and quantum effectively goes the way of the Betamax. But I can't see that at the moment, because there's nothing that I've read up on that's even remotely close to where physical quantum is right now as that next step.
Quantum Betamax. Now that there's the mashup nobody wanted.
Yeah, exactly.
So I had a question about the market for quantum computers in the future. So my thesis going forward is that quantum computing is emerging in a very different kind of market where the world is already shot through with classical compute that's solving all kinds of problems. And so I've been operating under the assumption that there would not be a whole lot of market pressure or demand to develop personal quantum machines, because you will just be able to hit an API and all that infrastructure exists and there's no need to kind of do it. Whereas with the personal computer, with classical computers, that was not the case. Like, these things didn't exist. And so it made sense for you to have one in your office. Not to say that with room temperature quantum computer, there wouldn't be markets for it. People would want to own it and mess around with the hardware directly themselves. Yeah. But well, I mean, have you given a lot of thought to what the ultimate market would be in light of, what I just said? Do you not buy that?
I mean, it's hard to determine just how big that market will be, right? I guess it comes down to how well perceived quantum becomes over the next few years, right? The more we get towards that room temperature quantum, I think we'll notice a big change, because some people that might not be able to afford to get into that kind of environment, obviously buying something that you can run at home. I mean, we're seeing that with LLMs to this day, right? So obviously ChatGPT was a massive hit for a lot of people, but now people are running LLMs from their own home networks so that they don't have to use and pay for those services and give all of their data away. And that's a big shift, right? We're not talking about having all of that AI be effectively centralized on one data center or multiple data centers owned by the same company anymore. Now people are sort of smartening up about it and going, actually, why am I giving all that company my data? Why don't I just run the LLM from my own machine here? Yes, it'll be a little slower, but it'll still work the same way. And suddenly it drives new interest in that subject, right? And I think we'll see the same with quantum, is that there'll be a few really cool case studies that hit the market that'll drive people's, imagination into what quantum can truly do. And then suddenly we'll see a little bit more of it carved out for itself. And like I say, we don't know where it'll end up, but I really hope from a next step perspective that something comes after a PC, because we're going to hit that point of no return where it doesn't matter how much we try, you're not going to squeeze any more out of a CPU. We're probably, I would say, we've probably got no more than 10 years at the rate of development in CPU technology before we hit that kind of scale where you're going to just get diminishing returns. And then what's the point in buying a brand new CPU the following year when you're not going to get even 0.1% uplift in performance?
Do you think Moore's Law's got 10 years?
From what I see, from how certain chips are, yeah, like it's really bad. I don't know if you've actually looked into some of the processors for server grade equipment, right? Server grade equipment has jumped from like 200 watt CPUs to like 550, 600 watt monsters now. And that just makes no sense to me. Why are we getting to the point where we've gone from having really high end, like power hungry CPUs, then we went down to the really ultra efficient, and now because we're hitting that cap again, we're just pumping more power into it because we can't build fabrication units that can go down even smaller. I think we're locked at around 5 nanometers, something like that. Any smaller, you need to rebuild the technology again. So who's going to spend that kind of money building out a fabrication unit to maybe get an uplift of 0.1%. They're not going to spend that nobody's going to justify spending that kind of money on a fab. It's one of the reasons why it took so long for Intel to finally pull the trigger and build their fabrication unit in the States, because up until they got forced to, they had no need to. So, of course, America didn't really have many fabrication units compared to, say, China. But then, obviously, embargoes happen, trade problems and stuff like that, and suddenly whole world has a chip shortage. Now, suddenly, everyone's like, oh, we need to build fabs because the amount of money there is in it, suddenly it makes viable sense. So I'm hoping that, 5 years, 10 years, we'll see something next generation come along. Whether that be quantum or something else. It's just getting to the point, though, that where we're going to have to redefine some parameters around what general purpose computers are.
Okay, let me speculate for a little bit here.
Sure.
Just a couple of years, I think we'll have robots that start doing a lot of things in our lives, humanoid robots, and then we probably going to go down the path of turning them into flesh bots, and we're going to create surfaces that we can grow skin on them to make them more human-like, and it'll start kind of like a chia pet, and go from there as we add more and more layers onto this. But these things will, either they will wear out or they won't ever wear out. and so then we decide how these things are going to fit into our lives. Are they going to be tools for us to use? They're going to be friends with us? Are they going to be replace us? How does that fit into the world around us? And I'm sure you guys are thinking about this stuff all the time, right?
Actually, speaking of robots, we've just ordered one that's fully open sourced. We're going to try doing some reinforcement learning using quantum restricted Boltzmann machines on Dynex to actually train it and learn it. So yeah, that's going to be a really fun one, especially when I go take it for a walk down the road with me, just for the sheer fun to see what all the, everyone thinks of it. Because it's a 6-foot robot, basically. It's up and running around. So yeah, it's going to be some serious fun, that project.
You should be able to change the height so that they're not taller than you, right?
Well, I'm 5'10", so I don't mind. 6 foot's okay. There's not much difference in that regard, but yeah, it's going to freak a lot of people out when they become more mainstream again, right? Robots are still quite expensive, but they're coming down in a very sharp rate. Like, it was only a couple of years ago that if you were looking at any kind of robot, it was 30 grand starting price. Now you can pick up, basic robots like, the type that they used for going through tunnels and stuff like that. They're like 3-4 grand now, and a full upright humanoid style robot now is 15 grand. I mean, it's not going to be long before they become to the point where they are affordable for everyone to use. To me, it's just, the question is who's teaching them and what are the morals like of those people teaching them? Because quite honestly, that's where it gets really quite in a dangerous area, right? Because if they're all trained off of one data set, who's trained that data set? Is it somebody that's all about the science? Is it somebody that has a military background? Is it somebody that, just wants to watch the world burn? Because each of those are going to affect how those robots react in the real world.
I have a somewhat technical question. I've done reinforcement learning in the past. I was an RL engineer at an aerospace exploration startup, and I'm curious, like quantum restricted Boltzmann machines, why that particular approach to RL?
That's a very much, that's definitely Sam's area of expertise. That's what he developed for Dynex, doing restricted Boltzmann machines on quantum. Really was his area, and that was already made before I even joined. But from my understanding, the ability to learn and do iterative learning using a quantum restricted Boltzmann machine is just immensely powerful and super efficient. We use it for, so we've got like an internal auditor solution that we built, me and Sam. We do like blockchain auditing, for example, on our spare time. What spare time we actually get, that is. But the reinforcement learning of that, or what we dubbed transfer learning, right, so that it was easier for people to understand what it was doing, works in this much in the same way as a human brain again, right? Short-term memory being the held in RAM on the PC, and then you do transfer learning, you do all the iterations, and you combine it into the existing data set, and then you restart the application with all those new data sets. So of course, we want to continuously run scans and then put all of that data back into our own machine learning algorithms that we've got running. So of course, that mechanism was just the ideal solution. And I think that we're going to at least start with that idea for reinforcement learning on this robot. But we might find that actually there's a better method. We're very open to doing all kinds of different options. We don't tend to tie ourselves to one avenue, because there's a few of us now that have very broad, and diverse backgrounds. So I might go take one type of functionality. Sam might go take another functionality. Claudia might take another functionality, and Adam might take a completely different one. So we try and generate as many avenues, because if you think of it like this, if I come to you with just one idea, if that one idea doesn't work, that's it. It's done. Right? You've already lost the person's interest. But if I come to you with 10 different avenues and go, try one of those should work, then the likelihood is already a greater factor straight away, right? Because you're generating multiple paths of research. And that's what we're always aiming to do, multiple paths of research.
All right. One last really bizarre question. Is it conceivable that all of our whistleblowers in the future will be robots that nobody owns?
That's a really interesting concept, right? So how do you protect people's privacy, data, all that kind of, freedom that we've grown so accustomed to, right? What happens if a robot gets hacked? Who's then responsible? Is it the owner that owns the robot, or the person who hacked it, or the person that built the robot, like the actual company that built the robot? Like it becomes an ethical dilemma. It's one of the reasons why Dynex had its own ethical committee, right, for these kind of exact scenarios, right? So if something gets flagged up by our security system, there are 3 stages in our security system for that, right? Green is fine. We use a traffic light system is the best analogy, right? Green is fine. Orange is that needs to go off to the ethical committee to say yes or no. And then red is outright blocked. And obviously, if they continue to upload code that falls in that red area for issues, then we then take the appropriate steps to contact that client, find out what their problem is, because it might be the way that our digital fingerprinting service actually, flags it. So there's always room for human error. Makes me laugh, given how much we're playing around with machine learning, that there's still human error involved in it, but there was something that Sam showed me yesterday. Well, not yesterday, actually, a couple of weeks ago now, and reminded me of it yesterday, because when I told him that I was coming on with you guys, is that he reminded me to explain Dynex code in Dynex, because we actually showed off a presentation of a web app coding Dynex code for to run quantum jobs by itself. So you give it the parameters and it will go and code all that for you. So it really is that next iteration step, right, where we don't even we take a hands-off approach at that point, and we can go, well, if you need coding help, you can just click a button here, and then up pops this, almost ChatGPT style interface that so many people are very familiar with. They just ask their question, and instead of it being all text related, it's going to be purely to do with code. So I mean, there's going to be some massive ethical problems though down the road with what robots, quantum, AI in general, or AGI, I think is probably where we'll see more problems with than just normal AI. I'm not a big lover of the word AI personally because we're not there yet.
Yeah.
Like AI is the wrong term. It's all machine learning. But I understand why people use the term AI because it's easier for people that might not be from a technical background to understand it. So obviously I always try and split the definition. So obviously I use AGI as well, which is what OpenAI is working on, right? The ability to do artificial general intelligence. So that would be where it starts to have that bit more freedom to start thinking for itself at that point. And I truly think the neuromorphic network could potentially give the possibility of an AGI because it is biology inspired after all.
Right. Excellent. Clifford, this was a very wide-ranging conversation. We really appreciate it. Where would you send people who, want to learn more about Dynex and what you guys
Yes, so we have our blockchain side, which is dynexcoin.org. We also have our enterprise side of things, which is dynex.co. From there, all of the white papers we've written, all the scientific papers, all of our research material is available. We open source.
Do you need a dynamic and knowledgeable speaker for an event? Thomas Fry and me, Trent Fowler, are both seasoned keynote speakers, able to converse on a wide array of topics to audiences of all sizes and skill levels. Go to the contact page at futuraudiopodcast.com to book Thomas or myself today, and let us apply our years of experience in public speaking to make your event a smashing success.
That some of our other devs have written, and you can just happily run them for free. As long as obviously you register for an account, there is a 7-day free trial of our services from an enterprise perspective. If you're on the crypto side, you can just pay with our crypto and run a job immediately. It really depends on how you want to do it. But we're also on X, although I don't like using the word X, it's Twitter. It's still Twitter.
It'll always be Twitter.
It's still Twitter. But yeah, if you search up obviously Dynex Coin, you'll see our Twitter feed. It's pretty active and posts pretty much every day new case studies that we're working on, new information, new research material. We announce obviously new partnerships via our X feed and stuff like that. So yeah, we try and make ourselves very readily available. Like I do a lot of YouTube interviews. I'll do live streams with people and just broadens people's minds into what is truly capable with blockchain and disruptive technologies.
Okay.
Beautiful. Well, thanks so much, Clifford. This was a fantastic conversation.
Thank you for having me.
Yeah. I encourage everybody to go check out Dynex and what they're doing. I thought you had great answers to the questions about the justifications for using all these cutting edge techniques. And we wish you the best of luck.
Thank you very much.
Thanks, Clifford.
Thank you.